Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to talk about electromagnetic induction, in which a movement or the change in a magnetic field causes a movement within the electric field. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description for the note of this entire discussion. So let's first talk a little bit about induced currents, since this will be our main topic within this entire discussion. So the idea is, if you have a magnetic field, let's say this is north, this is south, and then you have a coil. If you let the magnet move, this will cause a current. And the same thing is true if you actually do it the other way around. If you have this magnet and then you have this induced coil, the coil, and then it's moving, it will later induce some form of a current. So that's the first observation. But then we could actually take this a step further, since a magnet is technically just a coil pretty much. So you could pretty much have a coil, and then moving it will later cause another current in the other coil. But it doesn't only stop until there. What if instead we actually try to instead just change our I, so it's I as a function of t. So there's a changing magnetic field, and it turns out that it produces some more currents depending on your change of the current. So there's something to do with the change in the magnetic field, even though it might seem that it is related to the movement of the magnetic field. It's technically much more of a change in the magnetic field. So this is what we call as the electromagnetic induction. So a very easy way to describe such thing is by taking Faraday's law. So Faraday's law states that with the changing magnetic flux, it will cause a electromagnetic induction, or pretty much a electromotive force. So the flux here will be defined as the integral of b vector dot dA vector. This definition is very similar to the electric flux, in which you use phi e instead. But in here we'll be discussing for magnetic flux, in which in here it has a very specific unit, which you call as the Weber, or Tesla meter squared. Sometimes Weber is used for specific applications, but the way that you should actually separate between Weber as well as Tesla is that Weber describes the flux, while Tesla describes the field. So what is the Faraday's law exactly? So the way that it is defined on the textbook is that the electromotive force equals to the negative of the change in the flux. But this electromagnetic force is very relative. It could be positive, it could be negative, depending on where you put your positive and your negative. So instead, I will just straight away introduce the concept that this EMF is pretty much just voltage. So, well, technically it's negative voltage, which is defined to be the integral of E dl. So this is the definition that we'll be using a little bit more. So this will be the integral of E vector dl vector equaling to the negative d magnetic flux over time. So in here, technically the integral should be a closed integral, because the way that we'll actually use it is by actually looking at this entire pathway. instead of taking a particular path. We are taking a loop just to see if the potential is if the electric potential is conservative or not. And this is something that plays out within Kirchhoff's law. We should remember that using Kirchhoff's law, the loop should sum up to 0, or pretty much the sum of all of the potential should be 0. But in here, we see that if there's a changing magnetic flux, we see that there is a change in the potential, in the electric potential. So this is why we cannot truly use the Kirchhoff's law when we have a changing magnetic field. So now I want to try to actually use this Faraday's law for certain examples. So let's do something like this. If we have a loop of a wire, let's say, and then we give it a magnetic flux, in which the change of the magnetic flux in here is within this direction, which is greater than 0. Let's just state that this magnetic flux over time is always increasing. The question is, what will happen to the current and what's the magnetic field that is caused by this change in the magnetic flux? So let's first just write the equation first. Equals to E vector dl vector equals to the negative d phi b over dt. So we will try to define this L vector here to be the path going in this direction. So this will be our L vector. So we'll later try to get small cross sections so that we could sum it over the E vector, so it's dot as well. So the value of this thing should be negative. But we know for a fact that because this is radially symmetric, that means that at each point the electric field should be the same, and also its magnitude should also be the same. So it turns out that this would be pretty much like 2 pi r of the E vector equals to the negative d phi b over dt. Let's actually not use the E vector. So we could actually straight away determine what's the magnitude of the electric field. And not only that, we also know about the direction. The direction of the electric field should go in this direction. So this is our electric field. And remembering about the relation between electric field as well as current is that pretty much the electric field is always in the same direction as the current in here. Well, in here, that's the case because of this literal situation. So the current cannot go really past the path, so it must be contained within the path. And then luckily, because of the electric field is parallel to the path, that means that it's pretty much contributing to most of the current. So it's proportional to the current. And because of this current, we could actually use the previous law, or the Ampere's law, to determine what's the magnetic field. And observing this and using your right hand rule, you could determine that there is a magnetic field going into the screen instead of out of the screen. So we do see that the change in the magnetic flux will be countered by the magnetic field that is generated from this induced current. And this is what you call as Lenz's law. So Lenz's law pretty much states that the electromotive force will try to counter the change in the magnetic field. So let's do another example. Let's just have this piece of wire, and it is within a magnetic field going into the screen. This is all B vectors. until a certain boundary, in which I'll try to pull this out. So there's a velocity, and then there's no current. So it's just pretty much this one coil, and then we are trying to pull this out. That's the idea, and let's actually figure out what would be the power that is needed for us to bring this out. So let's just state that there's no gravity. So we could just state it's like pretty much being pulled out with the gravity being into the screen as well. So let's see this in between the conditions, in between each of the boundaries. So anything before it reaches the boundary, the magnetic field isn't really changing. So this means one thing, which is that there is no current. There is no current that is trying to resist, and thus there is no magnetic force. But when you are starting to cross this boundary, it becomes a different story. So let's just state that this is what you call as the length, L, and this would be the length, H. So here's something that we could actually try to discuss straight away from this formula, from the Faraday's law, equals to negative d phi b over dt. So we'll just keep writing this to be E vector dl vector, as I won't really change it yet. And this equals to the negative d phi b over dt. Now this is where it gets a little bit interesting in terms of the mathematics. Phi b is defined as the BA, right? It's the sum of the magnetic field over the area. And if you have this wire here and it's crossing a boundary, this value here, so if this is H and we are pulling it by V, this area is pretty much L times something, right? L times a H prime, let's say. But we know a relation between H prime as well as a V, in which H prime is the negative dV over dt. Well, an easy way to actually to state about this is that it's pretty much telling about movement. Well, it is obvious that the H prime should reduce proportional to the speed. So this is the relation. So we can write this as the negative d over dt, b, multiply that by the area. And because everything is perpendicular, so we don't need to write the cosine or the sine of something. So it's the area, which is the length, multiply that by h prime. And luckily with this relation, we are able to obtain that this E vector, the L vector, equals to B times V. Oh, sorry. So this is the wrong way. So it's this d over dt. Sorry, this should be BLV. So this entire thing is defined to be as our EMF, right? And so let's actually think about this. The wire is not really a superconductor. Well, technically, every material has some form of resistance, but it could be close to zero. But in here, our resistance is not zero. So that means that we could actually determine what's the current that is flowing within this coil. So if we use Ohm's law, we would get the EMF over the resistance, right? And this would later be BLV over R. So now the question is, in which direction does the current flow? So we can still use our Lenz law, because we know that because we know that the magnetic field is going into the screen and then it's decreasing. It means that it is as if that there is this magnetic flux going out of the screen. So using your right hand rule, it should be within this direction, but because it's the negative, it will be in the other direction. So it will be in this direction. This is where the current will flow. So we can determine what's the power that is given from the magnetic field in itself. So remember that power is pretty much the EMF multiplied that by the current. This will be B squared L squared V squared over R. So this is the power that was generated by this magnetic field. So in order to obtain a constant V, we would need to pull it with a certain force. So let's determine what the force is just by using Newton's second law. So because we already know what's the current, we could actually use the previous formulas to determine the forces on each of the wires, on the straight wires. So remember that the force is I/L vector cross B vector. So we could use this here. So let's determine that the L vector is in the same direction as the I. So for the one in this direction, the L vector, no, let's just use a different color. Let's use red. So within this direction of L, we could determine this to be IL dot B, cross B, sorry. And using your right hand rule, it will go in this direction. This is the force. And what about in this other wire? Well, the only change is the direction of our L, which means that it will be going in this direction. So we see that the force going downwards as well as upwards pretty much cancels each other out, which means that it's not moving or it's moving with a constant velocity. Same idea within the x directions. So in here there is no force, so that means that this is where we give force. So this is the force from the external. So we're trying to pull this out. But then from here, if we actually try to use this direction as our L, and then using your right hand rule, we determine that the force is going in this direction, and the value of this force is BIL. So remember here that this length here is just a notation from the formula, but in here the length is the literal length from the top to the bottom. So that's the force. So power, remember, was force multiplied that by the velocity. And because we know about the force, we could write this as BIL times V. And then we also know what the current is, so we could just substitute this straight away. It's B squared L squared V squared over R, which means that we actually conserved energy. So at least the energy isn't going anywhere else. So we know that the entire energy is only used for the magnetic as well as our mechanical force technically. So this idea could be implemented for multiple things, but one thing that is popping up is the idea of generators. So the idea of a generator is that if you have some piece of coil, and then we would have a magnetic field, let's say, within maybe like, yeah, within that direction. So if we actually try to apply a mechanical force so that this thing will rotate. So let me just draw this in a much more better way. So if we have a magnet in here that has magnetic field within this direction, and then we have this piece of coil that we could turn. What's gonna happen is that we know that the B vector would be constant, but the A is not a constant. This is changing. And this changing area will later determine what's your changing flux. And this changing flux will later be turned into our EMF, which is like a battery. So this works as like a generator in which you could actually create a potential difference from mechanical work. This is pretty much a conversion of energy. You could convert your mechanical work into a source of electric energy. So I won't fully discuss about the full mathematics, but you could make a model for you to figure out what's the EMF as well as the current that is flowing through. So now I want to discuss a little bit about eddy currents. So what is eddy currents exactly? Eddy current is a current that is formed from a changing magnetic field in a piece of conductor. So if we have this conductor here, this conductor is filled with electrons, right? And so you could actually apply a changing magnetic field, and according to Faraday's law, there should be a EMF, thus causing a current within this material. So let's just state that I put a magnetic field in this direction. That means that it should be traveling in the opposite direction. So there will be loops within this entire conductor or a sheet, and the current doesn't have to be circular. It could be in any direction that it wants, because pretty much it is as if you have lots of paths for you to do a circular motion type or a loop. So there are multiple paths, and this is what you call as the eddy currents. And that the idea is that you could actually control the amount of eddy current that exists in the material just by changing its shape. So maybe this thing here has lots of eddy current or eddy loops. But maybe if you actually instead have this guy, but then you cut some of the slits here, instead it will be much more localized. So there will be less eddy currents, and thus there will be not having lots of induced currents within this material. So this will later be observed when you're making like a brake. So there's this idea in which if you actually have this metal and then you chuck it into somewhere in between two magnets, so there's north, there's south, there'll be a changing magnetic field because of the area that is. So it's like the BA, and then the A is changing because of the cross section. And so with this changing magnetic field, it will later cause eddy currents, or pretty much the current that is generated from the EMF. And this would later have a force going in the opposite direction, which is pretty much similar to the example that we already discussed. So there will be a much more higher force. But if you cut slits into this, there are less paths. There are less loops for eddy currents, thus reducing the break. So it could be stated that it would be almost like there is no break. It could be like going past through. It will be just going straight through this current. So applying this idea further, we could just state about two different types of loop, open and closed. So for closed, if there's a potential difference, there should be a current. Let's say in that direction. But if there is, let's say if there's a changing magnetic field, but then the loop is open, what ends up happening is that there is charge buildup. And this is where you could observe your EMF. So you could just measure the voltage in between these two, and that's pretty much your EMF. So now I want to talk about pretty much inductance as a whole. So inductance is pretty much the same idea in which you're dealing with changing magnetic field, but instead we'll be doing it in the perspective of currents. So there are two types of inductance. One of them is what you call as mutual inductance, while the other is self-inductance. So mutual inductance is the same idea as the one that I presented earlier, in which if you have a coil, change its current, it's going to be felt by the other coil, and this will be discussed in the next chapter. But in here, I want to talk about self-inductance, in which the changing magnetic field results in the change of current within itself. So how do we quantify a self-inductance? So we will denote something which you call as the self-inductance ratio, pretty much to be the magnetic flux over the current. So if there is a higher current but a lower magnetic flux, it means that it has lower self-inductance, and vice versa. So this pretty much quantifies the change of the current into magnetic flux is how big. And the unit is what you call as Henry, or it's pretty much the Tesla meter squared over ampere. So let's actually do a very simple example of an inductor. So it's pretty much the same coil, and let's say you know the length, and then you know what's the density of the loop. And let's say that in this starting there's a cross-sectional area of A, and you're supplying current I. So N is density. So the way that we could actually solve for the self-inductance is by actually determine what is the magnetic flux first. So we know that the magnetic flux for a single loop would be BA. But then there is N times L, which is the amount of loops that exist within this one solenoid. So this is our magnetic flux. But we could do better. We know what is the magnetic field, thanks to Ampere's law. So we have already done this computation for our magnetic field, and it turns out that the value is mu0 and I. This is our magnetic field. You multiply this by the area. And so if you would later divide this with I, you would get mu0 and squared L A. So this is the inductance of a coil, as long as you know all of these parameters. So now, after we have already defined what the self-inductance is, we can actually do something very clever to our Faraday's law, in which d phi b could be transformed into the d over dt of Li. But since L is a constant in here, so we could extract this out to get L di over dt. And this is our negative of our EMF. So this is normally how it is written. But sometimes the positive and the negative terminal could sometimes get mixed up multiple times. So it really depends on your It really depends on your reference point and how do you solve circuits. So a general rule of thumb for me to use is by actually doing this. So this is inductor, this is resistor, and then capacitor. So in here, the way that I would define this voltage difference would be from positive to negative for each. Something like this, and then there's current passing through the positive terminal. This is how I define things. And you could determine what's the voltage difference here to be L di over dt. For resistors, it's straight away IR. And then for capacitors, the current is C dV over dt. So from my definition, it's everything is positive as long as you put everything in the right order. If you mix up the terminals, you could get a negative sign within every single thing. So it's better if you try to find a system that works for you. So maybe we should try to use my notation to solve a certain kind of circuit. So I'm gonna make a circuit in which it will be something like this. Oh. So there will be a current there, and then whoops, there should be a inductor. You know what? I'll just put the inductor here and connect it here. So let's just put an EMF there. There we go. So we have a voltage supply. Let's state this to be V. We got a resistor with R and an inductor L. So let's state at time 0. So after a long time, and then when time equals to 0, it's still within this. It's still within this condition in which it is connected straight away to the RL circuit. So there's no force that is supplying energy to this into our system. So this is where the condition, the current is 0, comes in, because there's pretty much no current going through. But then because of a change, let's state at time 0, we'll just switch this on. We want to figure out what's the change in the current. So what's the function of the current with respect to time? So let's try to solve this. Like normal, I will define my positive negative first, and my loop will go in this direction. So this is pretty much the current of the entire circuit. So this would be, using my notation here, this would be negative V plus IR plus LdI over dt equals to 0. So from here, what we could see directly is that this is a normal differential equation. So we could just figure out the homogeneous as well as the particular solution of this system. So let's just do that straight away. So the homogeneous solution in here is AE to the power of negative R over L, T. So I won't fully discuss how do you actually solve a differential equation, but you could later check foundational mathematics to solve differential equation. It would be about chapter 8, I believe, or chapter 10. So anyways, after we have solved this homogeneous solution of the differential equation, we could find the particular solution. And it turns out that one particular solution is that you could just state the current to be V over R. And this works. So combine them all together, you would get V over R plus AE to the power of negative R over LT. This is our current. And so what we could do now is is that we could actually determine what is this A from our initial condition, which is when time equals to 0, this I should be 0. So this is as if that 0 equals to V over R plus A. So we know what A is. So it's V over R, 1 minus e to the power of negative R over LT. So the curve is as if at time equals to 0, our current will be going up like this until a boundary condition of V over R. So that's for a RL circuit pretty much. And you could also determine what's the voltage in between the resistor or even the inductor based on our definitions of the potential difference. So let's just state that we have already kept this current for a unlimited amount of time, and then we want to switch it back to 0. What would happen? So we just need to make the same type of Kirchhoff's equation because there's no changing magnetic field. Let's just assume that to be negligible. So what we would get is the same idea, IR plus LdI over dt equals to 0. Now this is pretty much just a differential equation again. It's a e to the power of negative R over LT. And remember, at time equals to 0, in here, the current will be V over R. So it is still continuous. So it turns out that the current is just V over R e to the power of negative R over LT. So you could just prove this just by checking each of the voltage anyways, and the graph later turns out to be something like this. So it's also dwindling down until its stable point. So this is really dependent on the initial condition. So pretty much from this you could actually create very interesting waves. You could make a square wave or something like a shark fin wave. But because this is not really a electrical engineering channel, so I will leave it later. But if you want these kinds of discussion, you could go ahead and write it in the comments for me to discuss a little bit further. So now I want to discuss a little bit about magnetic energy. So we know that magnets create a force, but we haven't fully discussed magnets being magnetics as some form of an energy. So we could actually do this by actually using the previous example of this type of circuit. So the first thing that I want to write is that what is the power on each of the elements, and they all should add up to 0. So we got the V multiplied by I, this is the V of our source, plus the V times I of this guy, which is I squared R, that's the same thing, V times I, you can substitute this with IR, plus the energy in here, which I'll just denote that as V times I first, V of the L times I. And this value should still be 0. So this VL in here pretty much denotes what's the power that is being done or that is absorbed by the inductor. And this can be written further into Li di over dt. This is the power. But we know how to get energy from power, which is just the integral of power with respect to time. So if we do this, we would get Li di, this integral. So now this integral of Li di is half Li squared. This seems familiar because this is very similar to our energy of half Cv squared for capacitors. So it turns out that inductors also store energy in the form of the magnetic field. And we could actually bring this into a much more general case. So the U in here, which is half Li squared, if we use the definition of the inductor previously, we know the self-inductance of a coil is mu 0 n squared La. So L is mu 0 n squared La. So we could rewrite this as mu 0 over 2 n squared La I squared. Now, you should also remember what is the definition of the magnetic field as well, because this is where the energy is stored. It is within the magnetic field. The value is mu 0 and I. So we could just collect all of the mu 0 and i's. Mu 0 and I, we could square that. We could divide it by mu 0 just to keep it the same. We got La. Now, this is b squared over 2 mu 0 times L times A. And this length times the area is what is called as the volume. So we could do something now. We could define the magnetic energy density to be b squared over 2 mu 0. This is the energy that is stored in a magnetic field. And then you could later do a integration over the volume to get the total magnetic energy. So, from the book, we should be talking about induced electric fields. But in here we have already discussed about the induced electric field within Faraday's law. So I won't go fully deep into the understanding of induced electric field. But in here I want to discuss much more about diamagnetism, because this is a unique property when you're dealing within material science. So remember last time we have paramagnetics, we have ferromagnetic materials, but we also have diamagnetics, which is something which we haven't really discussed why it works. So I will dive deep into the quantum a little bit, and here's the idea. If you remember that atoms pretty much have electrons spinning, and just to make this simple, we would have two types of spin. One of them is going within this direction, the electron, and the other is going in this direction for the electron. So this is like the left-hand rule because it's technically the negative charge. So it's producing some form of a magnetic field. So the spinning creates a magnetic field. And so for a neutral molecule, let's say, for example, if we could discuss probably nitrogen, or you know what, we could actually discuss a little bit about nitrogen. So nitrogen, if you go a little bit into the quantum, nitrogen has seven electrons, which means if we actually fill it up within these shells, we would get something like this. So I will fully discuss as to why we could actually create something like this, because this is fully inside chemistry. But for now, I want you to accept this first. So nitrogen has has something like this, in which there's like this up and down. So this up and down corresponds to these types of spins of the electron. It could go clockwise or counterclockwise. Now, if you take a bond of nitrogen and another nitrogen, so it's something like this. The topmost electrons, so pretty much this thing corresponds to energy, pretty much. So this energy in here will later combine into another energy level in which it has all of these up and down. So one of these up and down corresponds to this kind of relation. There's one going clockwise, the other one is going counterclockwise. But we cannot fully state that the one going up is clockwise and then the one going down is counterclockwise. It doesn't work like that. But instead, this is our analogy. This is not a perfect analogy, but it works. So if we have something like this, and then let's just apply a magnetic field and see what would happen. Let's state I want to put a magnetic field within this direction. So there's a changing magnetic field. What's gonna happen is that because there's this change of magnetic field much more deeper, so that means that we have the d phi b going much more deeper. So it's going into the screen. So using Faraday's law, you could determine what should be the orbit is gonna be, because it's pretty much related to current. No, sorry, it's not about, yeah, it's pretty much talking about orbit, but in terms of the speed or the current. So if there is this magnetic field going much more deeper, what's gonna happen is that there should be a electric field, no, sorry, the current. So there's a opposition current going the other way. So it will be something like this. Now, this results into something else, because this pretty much what we'll call as the driving current is going to be added up with the original current, or pretty much the speed of the electron. And remembering that the direction of current is pretty much anti-parallel to the direction of the electron, that means that the movement of the electron will be driven in this direction. Now, this would mean different things. In here, the magnetic field will go bigger because the velocity in here is added up with the velocity of the original electron, thus making it much more faster. So the V increased. But in here, our magnetic field going in this direction will weaken. And this is because of the original velocity going in one direction, and the driven velocity is going the other direction. So it is weakening its velocity. And what happens in total is that the magnetic field is, so the sum of the magnetic field goes within this direction. While in here, its net magnetic field is 0. So we see that there is something different going on. And not only that, if we actually observe this with this magnetic field, we see that the direction is different. Which means that if you try to measure the magnetic field across this material after you apply another magnetic field, it feels like the magnetic field is like increased, or technically decreased if you're measuring it within the material. And this is because of this sum of the magnetic fields. So I know this the discussion is much more complex to the one in which we described for electronic materials, but it's fine because because magnetic relations is like very complex to understand. But but I hope with this video, I hope that you could understand this in a much more deeper context as to why you have ferromagnetics, paramagnetics, as well as diamagnetics. So that's all for this video, and thank you very much for watching, and also don't forget to like and subscribe, and please share this to your friends so that they can fully understand physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.